Roots by iterative methods, part 2. What we're going to look at today is what's called the Newton Raphson formula method of estimating or finding roots. And Newton Raphson's formula is simply stated in the advanced version of Third Maths book. There is no derivation of it, just simply stated. If what it says is, if little r1 is the approximate value of a real root, so we're looking at starting off with an initial guess like we did with the bisection method. So if r1's the approximate value of a real root of an equation fx is equal to 0, then our closer approximation to the root r2 is given by, and then we got the formula there, r2 is r1 minus the function's value at the value r1 divided by the derivative's value at r1. So it should be, from that, be apparent that the method can be used on any function that you have the ability to differentiate. If you come across a function you find you can't differentiate it, you would have to revert back to the bisection method of estimating the roots. So, going back to we're going to go back to a function that we found the roots using the bisection method last week. 5x squared plus 11x minus 17 is equal to 0 for x to 3 significant figures. When we solved this function using the bisection method last week, I took a look back and I've got it written down there, but I haven't. But the idea is we can compare how many iterations we took last week, which I'm sure you'll be able to tell, and how many iterations we take with this method. So, copied something across because we still require an initial estimate. We could use the graphical method or the function looking for a change in sign. There's a change in sign from positive to negative between x is equal to 1 and 25. So x is equal to, 1 and 2. So we've got a root somewhere between 1 and 2. So we've got this function 5x squared plus 11x minus 17. First thing we need to do is find f dash x, i.e. differentiate it. So with a further video, find the value of the function at the first guess, there, minus 1. Value of the differential of the function at the first guess, 21. Applied Newton Raphson and got 1.048 to 4 significant figures, which rounds to 1.05 at the 3 significant figures we're looking for. You then apply this value in a second iteration to find the value of the function and the differential at that value. You get these two values here. Put those back into Newton Raphson and come out with a new estimation to the root of 1.047, which rounds to 1.05, the 3 significant figures. Because we got that same value twice on 2 iterations, we can stop. As you reliably informed me, that took 6 iterations by bisection method last week. This time, I've done it in 2 with the Newton Raphson formula method. Don't think so. I mean, that's probably lucky. A lot will rely on how close your first guess is. Yeah. You have to be careful, I think, because if your first guess is too far away, and that's close to a turning point in the function, that can actually end up taking you away from the root. So you have to be a bit careful with the first guess. Right. So, problem 2. Use the Newton Raphson method to determine the positive root of the equation x plus 3 equals e to the x. This took 11 iterations using the bisection method. So what this problem is doing is finding the value of x when these two functions are equal, that point up there. So the first thing I had to do there was rearrange that so that it equated to 0, because we need the function equated to 0 for Newton Raphson. So there we got our function. Then find an estimation to the root, okay? And we found last week we had a root somewhere between 1 and 2, okay? And for a fair test, I'm suggesting we start with the same first guess as the root being when x is equal to 1. Yep. So have a go at that one using the Newton Raphson's method. So for those watching the video on the first example, our function is x plus 3 minus e to the x. Start off with a first guess of r1 being equal to 1. On the first iteration, function at 1 is 1.2817 and the differential is minus 1.783. Ending up with a new guess of 1.459 to the 4 required 4 decimal places, which is 1.7463. Second iteration, there we end up with a third guess of 1.538, and then on the next page I've actually pasted in the results from a spreadsheet that I used to do this to find that we get 1.505 for 3 decimal places after 5 iterations of the method. Looking at the next example in the notes, first equate the function to 0, find the first differential, and then this one took 3 iterations to find that the approximation to the root of 2 decimal places is 1.37. Is look at how in autograph you can actually look at how the bisection method and Newton Raphson's method home in on the root as you add iterations to the calculation. So what I've done here on 2 different graph pages, I've put the function y equals x plus 3 minus e to the x, which is the one before the last one we did, in autograph. Remember what we're doing, we're trying to find the value of x here when y is equal to 0. That's what the root is. So what we do is click on the function and right click. You see down the bottom here you've got bisection iteration and Newton Raphson's iteration. So you click on the bisection one, you get a new dialog box up. What we need to do is put in the parameters here. So we know we've got a root somewhere between 1 and 2. So we can put the parameters 1 and 2 in there. And then when we click, every time we click this button, we add an iteration to the calculation. So that's the first iteration when x is equal to 1. Second iteration, x is equal to 1.5. Remember, x is our guess of the root, so our current guess after 3 iterations to the root is 1.75, 1.625. Each time they're going in between previous one. That is bisection method. So if I zoom in on that area, carry on, we're looking for the result to be the same twice, 3 decimal places. There we have it, 1.505. So it's gradually honed in on that route down there, with the last iteration being that one there. Look at it. Sorry. So you can see from that how this software uses that method, or how that method actually hones in on the route as you add further iterations. You're making a guess in between the last two closest guesses. So you're being asked in the assignment to use that kind of software to demonstrate how each of these two methods home in on the route. So I'm showing you how to do that. So that's bisection method. I just click on the other page here. Again, select the function. Select the function, right click, Newton Raphson's iteration. This time there's only one parameter, first initial guess. We started with 1. And then as we do that, we add an iteration. So the next guess is 1.746. This line here is representing the slope, which is f dash when x is equal to 1. So you can see that this line here is the slope of the function at x is equal to 1. Add an iteration. We go back, we've gone the other side. So our new guess is 1.538. Move in a little bit. Add another iteration. We've gone in between again. So we're getting closer. 1 point. Maybe there. The last one. Exactly the same. So we can stretch this down and we can see all the results. So after 1, 2, 3, 4, 5 iterations, we get 1.505 with 3 decimal places. Yeah, if you don't have the skill, or there isn't a method in your armory to differentiate the function that you've got. Yeah. No, you can't. You can graph it to get a rough idea. So we go back. Let's put in the function that you've just been working on. Graph. So what's the function that you've just now done? Y is equal to 2 ln x plus x. So equating to 0, that's minus 2, yeah? So there's the function. So you can graph it, and you can see here that you've got a route somewhere between 1 and 2. Okay, so you could sketch it. Also, remember, use the function notation, starting at function with x equal to 1, x equal to 2, and look for where it changes sign. Remember doing that? Yeah. So if you can get a rough idea from that. You just keep doing that until you find a change of sign. Even the Newton Raphson's method requires you to have a first guess of where the route is. Okay. If I do bisection method on that one, we know we got something between 1, 2. So there's a first iteration. second, third, fourth. There we go. There's 1.37. 1.37. That would round to 1.37. If we're looking for two significant figures, the answer to that one is 1.37. What did we get? We did get 1.37, didn't we? Yeah? And the same function, so y equals 2 ln, what was it, x plus x minus 2. Newton Raphson's. Wonder what happened if we start with a guess much further away. So we can't, with this particular one, what can we not guess with? What values can we not guess with this function? What would be a bad idea? What would be a real bad idea? Anything negative, in fact, anything 0 or less. Because if you try and equate this function with x is equal to 0, try it on your calculator. Not like it. Not like it. So it's got to be positive, hasn't it? So what about if we guess, what did you say, 6? Overflow. Doesn't, even this doesn't like it. 3. 3's going to work. 1, 2, 3, 4. Same number, 4 iterations. From a guess at 3. Whereas with an initial guess of 1, so even if your guess is not that good, still generally quicker with this method. It just relies on you having this software, I recognise that, okay, or being able, and importantly, if you've got to show me how you've done it, you need to be able to differentiate. What you've been given to do, I'll take a question in a minute, Kurt. What you've been given to do in the assignment is a cubic function. You're not going to have any problem differentiating that function.